Wilson, go ahead. All right, Vanessa, go ahead. And who else? Julia, go ahead. And Aaron, go ahead. And Alisa, okay. Mr. Jake, go ahead. All right, looking good. Okay, so chapter 6 it is. That's we only have one chapter to take care for today. Then as you can see, you know, because we have 6 chapters, so the exam review questions, it's all about 47 problems. Sorry for that, but then there's a area that we need to do a lot of practice. That's the reason why you see quite a bit of numbers for section chapter 5, right? So but again, it's all good practice so that you can get used to the probability concept and the counting principle. Okay. Yeah, so if you be able to do all of that for a 6 problem on the exam review, you should be okay on the exam on Monday. Okay, but try to do those. Okay. All right, so chapter 6. So chapter 6, we looking at discrete random variable. So chapter 7, we look at continuous random variable. Then on chapter 6, we look at discrete random variable, meaning that we only looking for the occurrence of 0 time, 1 time, 2 time, 3 time, and so on. Okay. Okay, so now I would like to start out the definition of discrete random variable. Let's do this experiment, right? Suppose that we flip a coin 3 times and see if we can find all the outcomes of that. So from chapter 5, we know that we have to be 8 different outcomes, right? So let's see what we can looking after, right? So when we flip the coin for the first time, you get head or tail. Second time you get head or tail, and third time you get head or tail, right? So that's the logic we've been went through. All right, same thing with this guy, head or tail, and head or tail, head or tail, right? So when you list out all the combination that you can have, so my sample space will contain head, 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 and then head, head, tail, and then head, tail, head, and then head, tail, and tail, right? So that's the first half, and if I continue the other side, we have tail, 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 head, tail, head, tail, and then tail, head, and head, right? All right, so that will be all the 8 outcomes that I'm gonna expecting, right? Because when you from chapter 5, right? So if we look at chapter 5, if you flip 3 times, you have 2 times 2 times 2, so you have 8 outcomes, right? Which is what we expected, right? Okay, all right. So so that will be all the sample space that I'm gonna have. So now I want to find out, right? So I'm gonna let x1 to be the outcome, the entry, right, with 1 head, right, with 0 head, right? All right, so I said, well, since we have all the outcome listed, let's break them out a little bit. So x1 be the entry with 0 head. So how many entry do we see that have no head at all, right? Or zero head? Out of those are possible. Yeah, only one, right? So the only option that we achieving zero head will be a tail, tail, and tail. So x1 will equal to 1, right? If I let x2 to be the entry with one head. So now I only look at all the entry with one head. So how many are there with only one head in the system? List them out, and then we can count, right? Which one gonna be? I see tail, tail, and head, yes? All right, so you flip the coins 3 times, but you only see one head. The only thing that's gonna happen will be tail, tail, and head. Does that make sense? Okay, what else gonna be in there? Tail, head, tail, that's right. Tail, head, tail are gonna be in there because, you know, there's only one entry for the head. Is there more, or that's it?
Head, tail, tail.
Head, tail, tail. That's it, right? Yeah, so those are the only 3. So therefore I know x2 will be 3, okay? Now we will let x3 to be entry with 2 head. So now we have to look for all the entry contain 2 head, and the outcome will be head, head, and tail. Or I can have head, tail, and head. I can have tail, head, and head. So x3 also equal to 3. You guys stay with me on that? Yes? Okay. And then I let x4 to be entry with 3 head. And there's only one of those gonna happen is head, head, and head. So x4 will be 1. Does that make sense? So this is what we call a random variable. Okay, so a random variable is a variable that have its own definition or the descriptions. For example, if we're looking at x to be the event that contain all the head, then x can have 4 different outcomes, which is 0 head, 1 head, 2 head, or 3 heads. And that's how we define a random, discrete random variable, right? So a random variable is a single numerical values determined by chance for each outcome of a probability experiment. Random variables are usually denoted using a capital letters such as capital X or capital S, and then the possible value of that random variable are denoted using the lowercase letters, so S or little x. Okay, so for example, if I denote, right, if I let capital X be the number of head when we flipped the coin 3 times, okay? All right, so the capital X will be the number of heads when we flip the coin 3 times. Therefore, we have to look into all the possibility that X can have. And X1 will be, what happens if we have 0 chance of getting ahead? We get 1 of that. X2 will be 1 chance of getting ahead, and then X3 will be 2 chance of getting ahead, and X4 will be 3 chance of getting ahead. All right. So a capital X is a big description, and little x are the children of the capital X. So that's the logic that we should think about random variable. Does that make sense? Okay. Okay. So there will be 2 kinds of random variable. A discrete random variable, meaning that we're going to learn in chapter 6, and then a continuous random variable where we're going to learn in chapter 7, right? For example, that we saw just right now, it is discrete random variable, right? Now back to the example. In our 3-term cone flipping example, if we let x to be the number of heads appear in our outcome, then x is a discrete random variable, and the possible value for x will be 0 heads, 1 head, 2 head, and 3 heads. Yeah. So x is just a big box. Say I want to find out all the possibility of getting heads when I flip the coins 3 times. And then under the bars, right, there will be 4 people going out looking out. Okay, the first person will check out what is the chance of getting 0 head. The second person check out what's the chance of getting 1 head. The third person check out what's the chance of getting 2 heads, and the last person check out what's the chance of getting 3 heads. So that's the idea. Okay, so don't get mixed up between capital X and little x, right? All right. So for that, we can construct a discrete probability distribution for the event X. All right, so the event X will contain all the outcome that is going to happen, or the possibility is going to happen. So X can be 0, right? A little x can be 0, can be 1, can be 2, or can be 3. Okay, so we talk about 0, 1, 2, 3 here, right? 0 heads, 1 head, 2 head, and 3 heads. Now we can also find the probability of that happening. So if you look at the this situation that we just talked about, right? When I look out for the possibility of getting a 0 head, I know that I will get 1 chance out of that. So what will be the probabilities for getting 0 head? That's right. Thank you, Vanessa. So we have 1 out of a chance of getting a head, 0 head. Make sense? Okay. And now, what is the probability of getting exactly 1 head when we flip the coins 3 times? There you go. 3 out of 8. Right. And what is the chance of getting 2 heads when we flip the coins 3 times? Also, 3 out of 8. And what's the chance of getting 3 heads when we flip the coins 3 times? And that answer would be 1 out of 8. Right? All right. Questions, concerns, please ask.
I have a question. For 0, we still keep it as 1 out of 8, even though there's a very, very small percent chance of getting 0.
Yeah, because when you look at x1, the description for x1, so x1 equal the entry with 0 head, so we still have tail. So you have 1 out of 8 chance of getting that.
Okay, thank you.
Yeah. Yeah. So yeah, this is how we got those numbers come from, right? So x1 equal to 1, x2 equal to 3, x3 equal to 3 chance, and then x4 equal to 1 chance of that. Therefore, when we do the probability, we can take 1 divided by 8, and then 3 divided by 8, and so on. So don't get mixed up between x1 to be 0, right? X equal to 0 means that what is my chance of getting 0 head? So I get 1 chance of getting 0 head. So the probability will be 1 out of 8, right? So let me put that description for you. It means that what is the probability of getting 0 head? The answer is 1 chance, which is tail, and tail. And because of that, the probability x equal to 0 will be 1 out of 8. So that's how it's described. Okay, guys? So it's not, oh, why you got a 0 and you put 1 over a? No, 0 is not what we want to divide it by a. 0 is the description. What is the chance of me getting 0 head at all? You have 1 out of 8 outcome, which is tail, 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 and my chance will be 1 out of 8. Does that make sense? Sounds good.
Yeah. Can you scroll up a little bit, please? Just so I can write it down.
Are we okay with that? Probability distribution, yeah? What are you all right now?
Yeah, I'm all good, thank you.
No worry. All right, next. So now, based on the table, we can easily answer all of that question below, right? So find the probability of getting exactly 2 head, right? Oh, there's no formula, Vanessa. We look at the outcome only, right? So remember here we have 8 outcomes, and then there's only one outcome that you will not see any head at all, which is tail, tail, tail. And then because of that, the probability will be 1 out of 8. Yeah, we just look at that logic, right? There's no formula involved, right? Okay. All right. So now find the probability of getting exactly 2 heads, right? So the probability of exactly 2 heads is the same thing as P of X equal to 2, all right? So the probability of getting exactly 2 heads is the same thing as P of X equal to 2. And according to the formula, this will be 3 out of 8. Right, so when you look at the table, how many times I get exactly 2 heads? You can see here, you only get exactly 2 heads would be head, head, tail, head, tail, head, or tail, head, head. So out of 8 outcome, I will see 3 times I'm getting 2 heads. So that would be 3 out of 8. Okay. And for B, find the probability of getting at least 1 head for the example above, right? What does that mean by at least 1 head? Anyone?
7 out of 8.
7 out of 8. All right, Grayson, would you mind to explain that?
If it's at least 1 head, then basically the only thing we can't get is no heads. 1 out of 8, so 8 out of 8 minus 1 out of 8.
So I'm using the rule of complement, yeah?
Kind of. You could also just easily like 3 plus 3 plus 1.
Yeah, so that's direct ones, or you can use the rule of complement. All right, very nice, Grayson. Thank you for sharing. All right, so probability got at least 1 head will be P of X equal to 1 plus with P of X equal to 2 plus with P of X equal to 3. And according to the table, we can have 3 over A plus 3 over A plus 1 over A gets 7 over 8. Or you can use the rule of complement. So probability of at least 1 head will be 1 minus the probability that getting 0 head, right? And that's what Crescent was sharing. You can do 1 minus 1, 8. That's also give us 7 out of 8, okay?
So if there is no formula for this, how would we deal with incredibly large sets of data? Like, let's say we flip the coin 72 times and they want to ask how many different ways is it possible to get exactly 4 heads? Do we really just have to list it out and then be like, this many out of 72?
There's always something after, Grayson.
Okay.
Hang in there.
All right.
Good thinking ahead. Like, yeah. So now we only flip 3 times. So what happened? We're gonna flip 72 times. Are we gonna do that? The answer is absolutely no. Okay. You know, I think this is how all the statisticians in the past they will do the same thing. Now we have 3 chance. How about 100 chance? Are we gonna sit down and flip? I think they actually did it, and then they say, well, this is too much, so and then they invent a new way to do it. Yeah. I mean, we are very fortunate that we just use what they already discovered. Kind of makes sense, you know. Back in the day, there's no internet, there's no TV, so all they have to do is English or math, right?
I would hate to do it the long way. I would just say, no, forget it. I'll take the F.
Okay, all right. So now, how to calculate the mean, or the expected value, and the standard deviation of a discrete random variable. All right. So let's. So in chapter 3, we found the mean, the standard deviations of data, and you know, we technically we add them all up, and then we divide by how many they are. But in this chapter, we don't have all the outcome, but instead we have a scenario. We want to find, okay, you can think of, you know, the frequency, how many times it's happened, and so on, right? So here we have how many times you're gonna get a 0, so you get 1 out of 8 chance, and how many times you get a 1, you get 3 out of 8 chance. Therefore, to find the means or the expected value of a discrete random variable, we just simply take x multiply p of x. So we look at each description and we multiply its all probabilities, right? So by doing that, we should be able to find out how many are there, okay? And the standard deviations, here we take x minus the mean of x, square the quantities, and then time with the probability of x. Then we should be able to get the standard deviation. So don't forget, every standard deviation, we need to take the square root, okay? So standard deviation, we do need to take the square root. Okay, so now let's do it by hand and see how we would tackle this problem, right? So I'm going to use the same example so we don't have to spend time doing over again. So find the mean of this. All right, so the mean, the expected value, right, equal to x1 times with p1 plus x2 times p2 plus x3 times p3 plus x4 times p4 and so on, okay? So here I have 0 times with 1/8 plus with 1 times with 3/8 plus with 2 times with 3/8 and plus with 3 times with 1/8, right? Because we only have four scenario. We got 0 head, we got 1 head, we got 2 head, and we got 3 head. And each of that corresponding to its probabilities. Therefore, after we have that table, everything should be very straightforward, right? So to find the mean, that's all we do, right? We take 0 times its all probability, which is 1 out of a, and then 1 times with 3a, and then 2 times with 3a, and then 3 times with 1/8. Okay, so simplify, we should get 0 plus 3 over a plus 6 over a plus 3 over a. So that will be 12 over 8. So that's roughly 1.5. So again, this is all based on theory, right? So it just means that, right, if we flipped the coins 1.5 times in average, we expect to see one head. That's what it is. All right, and then the standard deviations. Right? So we call that sigma of x equal to x1 minus the mu square times p1 plus x2 minus the mean square times p2 plus x3 minus the mean square times p3 and plus x4 minus the mean square times p4 and everything underneath the radical. So sigma of x, just plug it in, you get 0 minus 1.5 square times with 1/8 plus 1 minus 1.5 square times with 3/8 plus 2 minus 1.5 square times with 3/8 and plus 3 minus 1.5 square times with 1/8. Okay. So again, we still look at all the possibility we are going to have for this. Therefore, we just said, yeah, we still have 0 chance of getting ahead, 1 chance getting ahead, and 2 chance getting ahead, and 3 chance of getting ahead. So we just put all of that together, and the mean we just found, and the probability is still 1/8, 3/8, 3/8, and 1/8. Doesn't change that concept, right? All right, plug into the calculator and see what we get. So this will be 2.25 over 8. This one negative 0.5 square that, so we get 0.25 times 3 over 8. This one same thing, 0.25 times 3 over 8, and this one will be 2.25 times 1 over 8. 2.25 plus 0.25 plus 0.25 plus. Right, we get 6 over 8, radical of that. All right, so we get 0.8660. Yes, Matthew.
When calculating the mean, why is it 0 times 1/8? It's the only thing I missed out on.
Oh yeah, because we have to look at all the possibility that we have. So we have to look at 0 head times probability of 0 head. Yeah.
Got it. Yep. There we go. Thank you.
Yeah, and then 1 head times probability of 1 head, and so on. Right.
Mm-hmm.
That's the description.
Uh-huh.
Okay, still feeling good? Yeah. All right, thank you guys. All right, so make sure you wrote those formula down so you can have the formula to play around with, right? So again, discrete random variable will be very straightforward. You can see how I constructed the exam review package. So on the exam, I'm probably gonna do that same construction. I'm gonna go from chapter 1 to chapter 6, right? So if you really go through chapter 2, the next question probably not gonna relate to chapter 2, right? So it's easier for you to figure out the formulas. All right, so the next example, I don't know why I chose it, but it's kind of a good application that we can see. Again, there are more detail into this kind of concept, but this one just very basics information here that we can always use. So when we talk about life insurance, right? So they can always give you any offer, a lot of offer. Talk about like you can do a 10 years term, 20 years term, or life term, right? So that's pretty much a lot of more information when you go into that detail. But here, just one example to demonstrating how it works in general, right? So suppose a life insurance company sell 250,000 1-year lifetime insurance policy to a 20 years old for 340. What does mean that there's no monthly payment? They just do yearly payment, right? So at the beginning of the year, you pay 340 and that's it, right? You have to take care of that anymore. All right. According to the National Vital Statistics Report, the probability that the 20 years old male survive the year will be almost 100%. So it's not that close to 100%, would be 0.9988734. Now, is this a good sell? Now, what does that mean is, for example, after the first year, you pay 340, and then, if the person happened to pass away, then the family receive 250,000, just like that. And then after the second year, the person pay another 340, and something happens, then the family getting 250 for that. But when you think of this logic, right? If you do 10 years, you take 340 times by 10, then you pay 3,400. If you do 20 years, then you double that. If you do 30 years, you double that. But even though we suppose that the person survived to 100 years old, so if you take 340 and times by 80, right? So that's how many years the person survived. It is nowhere close to a $250,000, right? So we making profits no matter what. However, if we are making profit, meaning that the company gonna lose money, but why do they still offer 250,000 lifetime insurance? What's the reason of that? So here we will look at how they make money. Okay, so it's a very simple one, and that's the reason why they can construct a $340 for the years, right? So let's go, right? So let's show you guys how it works in general, right? So we're looking at the probability of survive is 0.9988734. Therefore, the probability of not survive, right, will be 1 minus that. Okay, so let's see. We do 1 minus that. So the probability of not survive will be 0.001266, right? Okay, so take a look at this. So if the person survive, meaning that the company makes 340, right? If the person not survive, the company pay. So how much does the person receiving? 250K, right? However, gonna keep in mind that you don't really receive 250K because the person already pay out 340, yes? So in reality, the person don't receive 240K, right? 50K. The person, so the company perspective, they only pay out 250 minus the 340. Does that make sense? So that's how much they actually pay out because the person already take that money already, right? So the company actually paying 250,000 minus 340, right? So 249,660, right? So technically they pay you 250K, but in that 250K, the 340 already included, yes? So you don't really receive 250, you only receive 249,660, okay? There we go. So now we will take a look at the company perspective, all right? So then we will take a look at the company perspective to see how they expect it, right? So this is the company perspective. All right, so they want to find out the expected value, right? So when they find out the expected values. Remember, we have x times p of x, right? Plus with x1 times p of x1, all right? So that's that, x2 times p of x2. So in this case, we're looking at the scenario that we have the survive times the probability of survive, right? And then not survive times with the probability of not survive. And because the company is losing when the person is not survive, so they're gonna do that subtractions, right? So we get 340 times with 0.998734, and then minus 249,660 times with 0.001266. And when you do a simple math like that, so you get 339.57 minus 316.07. They making 23.5 on average. That's all they do. They calculate on average whether we're gonna make money or we're gonna lose money if we offer $340 per year. So they just calculate that simple, right? So if they take the money they will take in when the person survive take away the money they have to pay out when the person not survive, and see whether they will receive a negative or a positive answer. If they receive a negative answer, mean that they're losing money, so that's not a good deal. Okay, if they are making money, then that's a good deal for them. So, you know, in our perspective, we pay $340 a year. If we survive to 100 years of age, we're not paying anything close to 250,000. So both win-win, I would say. Yes. From their perspective and from our perspective. So, you know, a lot of people was thinking, should we do terms or should we do a life term, right? So again, depends on the people choice, but you know, if you do a life term, if you can do that, then you can see that in the long runs, you know, people still benefit from that, right? So you take, right, for you, if you take 80 times with 340, right? So the maximum we pay out will be $27,000 and $200, right? So that's after 80 years, right? From the year we're starting the life insurance, we still pay out $27,200, and you take that 250,000 away, right? You still benefit a lot, right? So this is their perspective. They say, oh, on average, I can make around $23.50 per person in the long run. So I should offer 340 to that 20 years old male. Does that make sense? That's their perspective.
I have a question. How come for the company perspective expected value, for that equation, it was addition was used, but then you subtracted the values? Like I get why you subtracted the values, but how come it's addition initially?
Because, you know, when subtraction means that they're losing the money. So they want to see how much can they take in, and then how much are they gonna expect to lose. So because, you know, they're not gonna adding, because when the person survive, they take in 340, but when the person not survive, they are losing 249,000. Does that make sense? So therefore, to balance it, you're gonna take what you get in and minus what you expend. So when you do, you know, when you do a business, right? So you have to take revenue minus expend to get the profit. Does that make sense, Julia?
Yes, so it's like situational of what you could do, either, you know, adding or subtracting.
That's right. You know,
Okay.
so when you look at your perspective versus the company perspective, right? You know, when you look at your perspective, then you would take minus 340, and then you would add 240, 9660, because, you know, if you surviving, you losing 340, but then when you not surviving, you're taking the money back, right? So this is the company perspective, and this is why we try to explain why they offer 340 a year and not like 350 and not like 300, depend on their perspective.
Okay.
That's correct, Grayson. Essentially, yes, it was plus a negative, right? So when you have a plus and a negative, that's turned out to be negative. Okay, sounds good. Yeah. No, Matthew doesn't like it.
I just don't understand the way you did it. It makes sense in my head just to make everything out by 1,000. So you go 340 times 1,000 and then 0.9 times 1,000 and then take that remainder and basically go 1.266 times 250, then subtract.
But where's the 1,000 come from, Matthew?
Just to make it easy numbers.
Well, when instead we have to look at the precise number, not the easy number, Matthew.
Well, it keeps it all the same. You're equating it the same.
Yes. Understand that. But then, you know, with that company, when you talk about like, you know, when they do business, $98, and then $1,000 is a lot of money, different for them, right? So
Yeah, but then you just
one or two person.
Yeah.
That's all. That's totally right, Matthew. Make life easier, right? Time everything by 1,000, so you don't have to deal with that. But just kind of give the student the detail here, how they, what is their visions from the life insurance company perspective.
Okay.
Mhm.
I think I'm getting this, but can we do another example of this to get it down better?
Yeah, I think there's one on the review and also one in the homework. So
Okay.
you might be able to play around with that. Yeah. So yeah, the reason I picked this one here because a lot of us say, okay, why do we learn this? When are we going ever gonna see that in real life, right? So this is just the reason I picked this one to demonstrate to you. Like a lot of people still think like. Still ask the question: is life insurance a scam, right? Why they give us so much money, given that we take in a little bit money from us? It's all because when the idea here is, suppose they have a million customer, and you take 23.5 times a million, right? So that's how much they're making over the years by selling life insurance to a million people. But then in that chance, not all that million people will pass away in the next year. That's not gonna happen. Therefore, they also take the money that we pay and then invest somewhere else. So they don't just do life insurance. For example, you need to have a loan. You can come to them and say, okay, I need to have $20,000 loans, and then they don't have the money, but they take the money from their customer and they give it to you, and then they take the interest. So technically they are the middle guy, right? So they say, okay, let's take Grayson 240 and lend it to Mr. Vo for 10% interest rate. So technically, you know, uh, you profit nothing, Grayson. They are profit for 10% from what you got. So every time they making $3.40 from your 340 payment each year. Mhm. And then when I have the money and pay them back, then something happened. They give you the back to you the money more than that. But again, that's not just one person. Yeah, so all we do right now is just some basics concept. Okay, if you really want to get much deeper into this, you can do an upper division major in statistics. For sure they will go in more detail of every single perspective a life insurance company can have. Okay. Okay, next up we have a 6.2. So 6.2 will be the answer for you, Grayson. What happened if we do the flipping the coin 72 times? Okay. All right, so 7.2, we focus on what is we call the binomial probability distributions, right? All right, so to become a binomial experiment, what is the requirement? So it will have to satisfy 4 requirements. Number one, there's only 2 disjoint outcome referred as success or failures. Now, back to the example of flipping a coin, right? So we only have 2 outcomes. You either get ahead or you don't get ahead. Does that make sense? There you go, right? So either success or failure. Or you look at the multiple choice question, you either get the correct answer or you don't get the correct answer. Or choose and fail, you either got that question right or you don't get that question right. There's only 2 outcomes. There's no middle, right? So that's the idea of 2 disjoint outcome, right? So if something have that description, it will satisfy as the binomial distributions. All right. Number 2, it have to be a fixed number of n trials, meaning that Grayson was asking, can we do 72? Yeah, absolutely, yes, it's just fixed. As long as you don't do infinite amount of trials, then you will always have the binomial probability distributions. All right. And number 3, the trials are independent, meaning that the outcome of one trial does not affect the outcome of the other trials, right? If I flip the coin the first time I get the head, does that mean that I flip it again, I should get a head? The answer is absolutely not. If you flip the coin the second time, you get a head, you are lucky. If not, you can get a tail, right? So that's the idea of number 3, right? So whatever happened in the first trial does not affect the second trial, and so on. And the probability of success denoted by little p, and the probability of failure denoted by 1 minus p is the same for each trial. So when you go back to the coins again, when I flip the coin for the first time, I have a 50-50 chance. When I get a coin for the second time, is that reduce my chances? The answer is no, it's still 50-50. And then I reduce the third time, I still get 50-50, right? So that's what it means by the probability of success will be the same throughout the trials. And then you look at multiple choice question, right? So suppose that question have 4 choice, and so you will have 25% of choosing the correct answer. When you go to number 2, how many percent do you have of getting correct answer? Still 25%. When you go to number 3, you still have 25%, right? So the probability of success at each trial will always be the same. So if any experiment satisfy those 4 conditions, we have ourselves a binomial experiment. Okay, if one of those fail, then it's failed. It doesn't work. All right. Is that explanation for the definition make sense, guys? There we go. All right. All right. So let's go ahead and take a look at the first example to see whether it's satisfied as the binomial experiment or not, right? All right. So let's check all the conditions. All right. So if I look at the first conditions, 2 disjoint outcome. You want to see whether it's good to go or not, right? So let's take a look at our first example. The number of people with plot O negative based on a simple random sample size of 10 is recorded. According to the American Red Cross, 7% of people in the US have blood type O negative. Okay, so you can see here, what are we looking at? We're looking at whether we have type O negative or no, not a type O negative. So that should satisfy, right? So the question is, do you have type O negative? Yes or no, right? I do have type O negative. I don't have type O negative, right? So they don't look for any other options. Does that make sense? So now we're only experiencing 2 outcomes. You have type O negative or you don't have type O negative. So that's the check mark. All right, number 2. Fix number of n trials. All right, when trying to see whether it's true or not. How many times are they conducting the sample? 10 times, right? Yeah, so they did it 10 times, so yes, right? Sample size of 10, so therefore it's fixed. So also good. All right, moving on to number 3. Number 3 said the trials are independent
Yes.
Yes, right?
Yeah.
The independence. And what's the reason is, if I get tap O negative, does that mean you're gonna get tap O negative, Graysons?
No. They don't affect each other.
Right. If you don't get tap O negative, does that mean that Aaron have to get tap O negative? No. Right. Yeah. So each of us, there's a possibility that none of us 10 are selective. We have no tap O negative at all, right? Yeah. So yeah. So so the first person have tap O negative. The first person have tap O negative does not mean that the second person must also have tap O negative. So therefore independent. So that's good. And then the last ones, number 4, probability of success is the same each time. Yes or no?
Yes.
Yes, right? Because if we are randomly selected, I have 7% of getting a tap O negative. How about you, Matthew? How many percent you're gonna have tap O negative?
100%.
Picking the wrong person. Okay, so this is funny. All right. Okay, so I have 7% of have a tap O negative. Matthew is the outlier, so don't count. Grayson will have 7% of tap O negative. Aaron will have 7% of tap O negative, and Walter will have 7% chance of get a tap O negative, right? Assuming that we don't know our blood tap yet, right? So therefore, the probability of success will be the same as a trial, right? So I know for now I should not pick Matthew to be in this experiment. Oh, that's not be fair because that will be a convenient sampling. All right. Okay. Does that make sense, guys? The answer is yes. Because each person will have 7% chance of tap O negative. Yeah, I don't even know what is my blood tap yet. I need to check that out. All right. Beside Matthew, have tap O negative. Anyone else have tap O negative? We don't know, right? So we all have 7% chance of tap O negative, right? That's very nice. Vanessa have tap O negative. Okay, so now there we go. Victor also tap. Wow, that's amazing. Wow. So, does anyone know what's the difference between tap O positive and tap O negative?
Don't O positive have like spike proteins where O negative is completely smooth?
Can tap O negative and tap O positive give each other plus or no?
I think O negative can like be given to all, and then O positive can take all.
That sounds right.
O positive can take all, right?
I think so.
But can they give to O or no? O
No, I
positive.
think that's only O negative.
Okay.
O negative can only receive O negative,
Oh,
and it can give to everyone.
okay, then I got it backwards.
That sucks. That's, Oh, Aaron also O negative. Oh wow, good. Yeah, I need to get into that. Which type of blood is like the most difficult one to get?
I think the most rare is like AB negative.
So they cannot get anything else. I'll give to anyone.
Oh, that could receive the least amount.
Hmm.
Oh, that would be O negative.
I see. Wow, interesting.
Something like that.
Okay, so now we have four students got okay. Victor have type O positive. Okay, so we have 3 O negative and 1 O positive. So the rest we have 7% chance of getting type O negative, guys. Okay, so yes, the first example will be binomial distributions. All right. So yes, this is binomial probability distributions. Okay. Yeah, so the check-in is that, right? So you want, this is good by in the way, because later on, if you are conducting a survey or something and you want, okay, I think I want to deal with binomial experiments, then you need to go through the list, right? Can I do that or not, right? Because, you know, sometimes using the wrong distribution can cause the wrong answer, right? Okay, so now it's your turn, right? Go ahead and see if B is also a binomial or not. All right, Matthew, very sure it's no. Okay. What is your opinion? What make it fail, Matthew?
There's no fixed number of trials.
Uh-huh.
And even the first one, I don't know it. I mean, it might cause, like, if one plan's late, that will affect the other one too.
Yeah.
Could, I guess. I don't know if that's actually a thing, but I know I believe number 2 is wrong.
That's right. Yeah, number 2 is a solid answer right there, right? The number of trials is not fixed, because if you read the statements, right? See, the persons randomly select fly until, right? Until she found 10 that was not on tab. It's not that select 10 fly, right? Yeah, so that's why it's not gonna work, right? Right. So the person can select 100 fly or 1,000 flight until she buy 10 fly that are not on tab. Therefore, the trial are not fixed. So not binomial. Okay, so when you have a feeling that this is not binomial, just look out for one counter example, right? So remember, to be a binomial, 4 conditions must satisfy. If one of those fail, the whole thing collapses, right? That's just like that. Okay, sounds good. All right, just a question. Almost lunchtime. Would you like to take a lunch break, or you want to go all the way until take a lunch break later? And then finish the class. I mean, end the class early. Or take a lunch break and come back. Okay. All right. So, all right, looking good. All right, let's take a lunch break, guys, and come back. We finish the rest of chapter 6. Okay. All right. So come back at 12:30 if you can, so we can get a. All right. Welcome back, everyone. All right, so yeah, a bit of introduction about binomial distributions. All right, let's go ahead and see how we can compute probabilities of binomial experiments, right? So to find the probabilities of obtaining exactly X success in n independent trials, right? So you want to find the probability of getting 5 correct questions on a multiple choice or 10 correct questions on a multiple choice, and this is how we do it, right? So the formula involved ncx p to the x powers, and then 1 minus p time to the power n minus x, okay? So this is the formula of getting exactly X success in an independent trial, right? For example, out of 20 questions, how many times I'm gonna get 15 questions correctly, right? So what would be my probability for that, right? Okay, so here's the example, right? So later on, I will show you how to make life easier using the calculators, right? But this is, everyone have to do it by hand. This is how it's worked, right? What is the probability of guessing exactly 2 correct answer in the 5 questions with 4 multiple choice, right? Okay, so n is equal to 5, and we want exactly 2 correct answers. So x is equal to 2, and we have 4 multiple choice. And what does that mean? So it means that little p will be 1 out of 4, right? Because of that. So the probability of getting 1 correct answer will be 1/4, because we have more 4 multiple choice in per question. Okay. So according to the formula, so therefore probability of exactly 2 correct answer is the same thing as we want to find p of x equal to 2. So this will be 5c2 times with 1/4 to the second powers, and then 1 minus 1/4 to the 5 minus 2. Okay? So technically, we want to find out what is my chance of getting correct and what is my chance of not getting correct. So that's why we do 1 minus 1/4. And if I have 2 chances of getting correct, then I will have 3 chances of getting not correct. But then we want to look in general, how many ways can I select 2 correct answers out of 5 questions, right? It just means that, it doesn't mean that you have to get the first 2 correct and the last 3 incorrect. You could get the first correct and the next 4 correct, and the last one is correct. So we have to look into 5C2, right? Look all the possibility you're gonna get a 2 correct answer out of 5 questions. Okay. Yes, Mateo.
I am confused about 5 minus 2. Can we talk about that real fast?
Yeah, so if you have 2 correct answer out of 5 questions, so how many times you're gonna get incorrect answer?
3 out of 5.
That's right. That's why they do 5 minus 2 in general.
But there's 4 questions or 4 choices, right?
Yeah, we have 5 questions, and each question have 4 choices.
Got it. Okay, I get you.
Yes. Yeah, you were thinking like 4 minus 2, right, Matthew?
Yeah.
Yeah, so we
basically.
have 5 questions, but then 4 multiple choice means that each question will have A, B, C, D. That's what they meant by that. Okay, and and here we go. We can use a calculator for what is 5C2, right? And then we just plug it in, and we should be okay. So that will be 10. We have 10 arrangement, and this will be 1/16, and this one will be 3/4 to the third powers, and then you put everything together, we will be able to get the answer when we wish, right? All right, so we are getting 0.2A16. Okay, sounds good. So to answer your question, Grayson, right? You want to get exactly 3 heads out of 75 coin flipping. Then you will do 75, choose 3, and then 1/2 to the third, and then 1 minus 1/2 to the 72, 2 minus 3, right? No worry. All right. So answer that, right? We another example. If we flipped 80 times, so probability get exactly, let's say 15 heads. So you do 70, you do 80, C 15, and then 1/2 to the 15th, and then 1 minus 1/2 to the power 80 minus 15. So that's what you want to do. If you want to find out what is my chance of, getting 15 heads out of 80 flipped. Good to go, Grayson. Hey, it's good to have that question in advance, right? And then I say, okay, now we can be able to answer that, right? Okay, so now binomial is something is very picky, right? So we will have to break it out into a few cases of binomial. We'll see that in a bit, right? So one thing that a lot of students get a confusion on is, okay, how do I know it's less than or equal or only strictly less than? So I kind of include here some useful terminologies and the translation to math symbol that we can see throughout the course of binomial experiments, okay? At least, no less than or greater than or equal, that all can be translated to bigger than or equal, right? You can see the math symbol. More than or greater than, there's no equal sign. Fewer than, less than, there's no equal sign. But when you see no more than, or like at most, or less than or equal, mean that you need to include the equal sign, okay? And exactly, equal or is always presenting as the equal sign, right? So those are the translation from the English phrase into the math symbol, right? So when you do your homework or the exam, just pay attention to those translation, because binomial is only take equal or less than or equal. It doesn't take more than, it doesn't take less than, okay? Very quickly. All right, so we will look at at least four different situations of binomial probabilities, okay, using our calculators, right? Now, as I mentioned before, if you want to find probability x equal to a, then the command you want to use in the calculator will be binom PDF. All right. And if you want to be less than or equal, it will be binom CDF, right? So there will be instruction for calculators, okay? I'm gonna show you right now how you're gonna use the calculator in for this section, right? It's only have two options. We have binom PDF used for exact. So used for exact X success, okay? Right, so the command you wanna do is, and then the other one would be binom CDF used for less than or equal only, okay? So it's only take the command of less than or equal. It doesn't have less than, it doesn't have more than, it's only take the command for less than, okay? So those are the only two options we can use for binomial theorem, by binomial distribution. So this is how we're gonna go it. So on your calculators, you're gonna press seconds, and then you press, I'll get press second step, right? You're gonna press second and you're gonna select vars. And then you can select, you know, binom PDF or binom CDF. So you have your calculator with you. You can definitely go back to that and see what's going on. All right, so let me share with you the calculators. All right, so here's the calculators. All right, suppose I want to do the other exercise that we just did. I just press second and then vars, and then I move the arrow all the way down until I see binom, right? So you see here, there's two options, binom PDF or binom CDF. I just want binom PDF because I want to do exact. They're gonna ask you how many trial was there. So we said there was 5 of those. And what is the little p? So we had 1 out of 4. And then how many times you get a success? So it was 2. And there you go, okay? If you have a TI-83, you live in that order also, right? You're gonna have it at N, P, and A, right? N, P, and A. If you have the advanced one, then they will ask you how many trials did you do, what is the probability of success, and how many times you want it to be successful. And that's how we got that one, right? There you go, okay? And if we do that again with the flipping a coin 80 times, right? Let's say we do it 80 times. And then this is on just 1/2. And you want to get 15 heads exactly. Then your chance will be 5.489 times 10 to the -9, which is very little, okay? That's the idea. Okay, so that's binom PDF, right? So that's how we use the calculators. Okay, so here the English phrase and then the math symbol and the calculator instructions. So I kind of put here in this box what we should do for each scenario, right? Because I don't know, I don't think the textbook kind of explain this detail. So when I wrote my note, I just kind of help the student out what they should do in each case, right? So when you have exactly equal or is, the math symbol will be x equal to a, and the command we are using will be binom PDF, okay? That's the only option we have. For example, when I have x equal to 5, then I will do binom PDF n comma p comma 5. So p presenting the probability of success, and then n presenting how many trials that we have. Now, in between, probability of A less than X less than B. So this one here, we're gonna do binom PDF of A, binom PDF of A plus 1, binom PDF of A plus 2 until you go all the way to B, right? So because we have to go from A to B, so there you have to go one at a time, and the only option we're gonna use will be PDF, right? One at a time. So here's the example. If I want to do probability between 4 and 6, I have to do binom PDF of 4, and then binom PDF of 5, and then binom PDF of 6. Because this is discrete, right? So we will not have like 4.1 or 4.2, right? We're always going to have 4, 5, 6 because this one is discrete random variable, okay? Now, when we have at most or no more than, the math symbol will be X less than or equal to A, and that's when you throw in binom, CDF, and PA. Okay, so don't get mixed up between, you can see the command here, they still ask you for N, they still ask you for P, they still ask you for A, but this up there will be PDF compared to this one is CDF. So meaning that it's gonna take everything from 0 all the way until A, right? Inclusive. That's the letter C stands for cumulative, right? So they're gonna accumulate everything from the beginning until that particular value. So if you can see here, when I have that example, suppose I do the same subjects, but I select in a CDF. All right, I still want 80. Right, I want to have 80, and then I want to have 1/2 for flipping a coin, and I want to have 15. So I will calculate it. So the answer will be much different, right? So what is my chance of getting at most 15 heads in 80 flipped, right? So I will have 7.05 times 10 to the -9. So the answer will be much different when you do see a PDF. Okay, so watch out for those little details, right? So that you don't use the wrong command. Okay, now what happened if we look at the restriction without the equal sign? So remember that binom CDF only taking care of less than or equal. Is taking care of anything else. So what happens if we have less than A? So how would we deal with that? If you have less than A, then the command still gonna be binom CDF, but now we don't use A, we're gonna use A minus 1. Okay, can you see why it have to be A minus 1 here? Yes?
Because we want it less than A.
That's right, because it's discrete random variable, right? So instead of saying like, okay, I have less than $10, I can just say I have less than or equal to $9. Yes? Yeah, so that's why we do A minus 1. So here's the example. I want to find out P of X less than A. I can do binom CDF and P4, right? So that's the idea of that, right? Okay, sounds good. All right, so what happens if we have bigger than? Okay, that will be that we have no other options beside the rule of complement. Okay, we have no other rule beside the rule of complement. So binom CDF only cover the area on the left hand side, which collaborate with the command less than or equal. So if we want to find the area to the right, bigger than or even bigger than or equal, we must use the rule of complement. For example, I want to find out P of X bigger than 5. I have to do 1 minus P of X less than or equal to 5, right? Or I want to do P of X bigger than 6. I'm going to do P of X less than 6, right? And then do a complement of that. That's the idea. Does that make sense, guys? All right, so keep in mind, this one is discrete random variable. So we're all going to go 1, 2, 3, 4, 5, right? So that's the concept, right? That we're going to try out. Okay, so let's go through the example, and hopefully we make more sense, right? All right, so the number of people with type O or negative, sample of size N, is recorded, right? So let's find out the probability of exactly 8 people with tab O negative, right? So fill out a few information. So we have N is equal to 10. Little p is equal to 7%, which is 0.07. Okay, so let's go through. All right, we want exactly 8. Right, so we have probability exactly A will be P of X equal to 8. So that's become binom I want to use PDF here because it's equal exactly A. So I will have N, P, and then A. Right? So in this case, I will use the command binom PDF. I have 10 sample of size 10, and probability of success will be 0.07, and I want exactly 8 out of that outcome. And that's what I want you to show your work on the exam. You don't have to use the formula here because this formula will be too much, okay? This formula is too much to handle. So this is all I know. I'll show you work on the exam.
If we did do it by hand, would the formula be 10 choose 8 times 0.07 to the 8 times 0.93 to the 2?
That's right.
Okay. Just wanted to double check that I understood.
Yeah, but then, if we have a large numbers of Grayson, when you do 80 choose 2, it's going to be big. 8 choose 80 to 15 is going to be big. Yeah.
Okay.
So better let the calculator handle that.
Okay. Sounds good.
Yeah. So on the exam, that's exactly how you show your work. Okay. Write out binom PDF 10, 0.07, A, and just producing the answer out of that. All right, so we're getting 2.244 times 10 to negative 8. You want to write it out, you write 7, 0, and the numbers. Just like that. All right, next up, I want to have at most 3 people, right? So probability at most 3 is equivalent to the statements x less than or equal to 3, okay? And that's equal size, so we can use binom C, D, F, and then 10, and then 0.07, and then 3. So this producing 0.9964. Still good on that, right? Yeah, still something that we don't have to play around with that much, right? So C is something they need to take care, right? Probability that more than 7. So equivalent to P of X bigger than 7. And we know we cannot do directly, right? So in binom CDF only take care of less than or equal. So this one here, we're going to use the rule of complement. So again, if we want to be more than 7, which one do we throw away? That's the logic. I want more than 7. So I want 8, 9, and 10. So I have to throw away 1 to 7. Make sense? All right. So this one equivalent to 1 minus probability of x less than or equal to 7. And that's I can use binomial. So I have 1 minus binom CDF 10.07 and 7. So this gives us 2.2a 2 times 10 to the negative 8. So it will be 0.0000222. Sounds good? Yeah, so when it's not there directly, we're gonna use logic to make it work. Okay, so that's something that we can do. So again, part D, we want to have less than 6 people, right? So we want to find out the probability of less than 6. So when you translate this to math, it will be P of x less than 6. So again, binom CDF only deal with less than or equal. So now we make the equivalent statement will be x less than or equal to 5. And that's when you can throw in binom CDF 10.07 and 5. So we get 0.99998. Does that make sense here, guys? Yeah, so I kind of give you all of the scenario that's going to happen, right? And then you can see exactly what's going on, okay? All right, so next on the list, we want to find out from 4 to 6 inclusive, right? So we want to have probability of 4 less than x less than 6. So that will be P of x equal to 4 plus P of x equal to 5 plus with P of x equal to 6. The only reason it works because this is still discrete random variable, right? We have 4 success, 5 success, 6 success. Otherwise, this concept will not going to work. All right, so we have binom PDF of 10.07 comma 4 plus with binom PDF of 10.07 and 5 plus with binom PDF of 10.07 and 6. And then you can put in that commands and then you should be on your way. Okay, so everything's rolling down. We get 0.0036.
Just to be clear, the formula that we got to do it by hand would only work if we need the PDF function on the calculator. If we need the CDF, that's a formula that we haven't learned yet, right?
So if you want to do a CDF creations, because when you think of the logic, right? So let me show you this real quick, right? So for example, you want to have probability of x less than or equal to 6. So this equivalent to p of x equal to 0 plus p of x equal to 1 plus p of x equal to 2 plus dot 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 all the way until p of x equal to 6. Yes?
Okay.
Then now you're gonna do 10c0 1/2 to the 0, 1 minus 1/2 to the 6 plus
Okay.
10c1 1/2 to the 1, 1/2 to the 10 minus 1, all the way until you get to 6.
Got it.
That's
Right.
why I don't want to show you guys that.
Okay. Too long.
Yes. What's the chance of student making mistakes? That's very big. So because when you do by hand, you're gonna write out everything, right? So to prevent that, let's use a command CDF, because command CDF will be accumulated. So it's gonna add everything from 0 to 6 anyway. So it will serve us better, that option. Yeah, suppose you want to find out the probability you're gonna get, at most 15 heads in 80 flipped, then you're gonna have fun with that, right, Grayson? But it's good to know the background behind it. So use technology, but it's good to know. Okay. All right. So now after that example, how are we feeling with the command in binomial experiments here? All right, remember there's only two options, PDF or CDF. CDF only take care of less than or equal. So you have any other situation, you have to somehow bring it back to less than or equal, yes? And don't think it's too much because it's discrete. So if it is less than 5, it's the same thing as less than or equal to 4, right? Or more than 7 is the same thing as 1 minus less than or equal to 7, right? Think of that logic very, very simple, right? Directly taught on that, okay? So don't think about what happened if we have a decimal. There's no decimal here, right? So don't think like, oh, less than 5 means I'm gonna go less than or equal to 4.9. That's not gonna work, all right? Because we still focus on discrete random variable. So discrete, we always go with 1, 2, 3, 4, right? 0, 1, 2, 3, 4, right? So think of that logic, okay? So it's not mean that, okay, oh, why Mr. Vo, when he did less than 6, he go directly to less than or equal to 5. What happened to 5.9? There's no 5.9 exists, okay? Discrete random variable. That's what we still focus on. Thumbs up now, guys. All right. Thank you. Thank you. Okay, so the last things in here will be, how do we find the means and the standard deviations of success P is given by the formula, right? So the mean will be N times P. So you want to find out, okay, I'm flipping a coin 10 times and the probability of success each time will be 1/2. Then what is my average? So when you take 10 times 1/2, it means that you're gonna get 5. So if you flip the coin 5 times on average, you will see heads right away, right? So that's on average. That's gonna happen. But again, when we carry out a real experiment, the result might be different. So this is all based on the theory, right? So that's what they calculated on. And the standard deviation for that success will be NP times with 1 minus P, and everything still underneath the radical. Okay, so this is only designed for binomial random variable. So we want to have N success X-independent trial and N success for that. Now, something that we're gonna use later on is this guy right here. If n times p, 1 minus p is bigger than 10, and n is less than 0.05 capital N, right? Then the binomial probability distribution will be a bell-shaped, meaning that we can use the empirical rule to identify the unusual observations. All right. So any observation that are outside 2 standard deviation of the mean is considered to be unusual observations, meaning that almost 95% of the observation will lie between mu minus 2 sigma and mu plus 2 sigma. So any other observation on the left of that or on the right of that will consider the unusual event. Okay, that's what it is. Because the chance of that gonna occur will be less than 5% of the time. So that's why we consider that's unusual observation. Okay, so you know, two standard deviation is good enough to contain everything. All right, so according to the American Lung Association, 90% of adult smoker starting smoking before turning 21 years old. So right there, that's the probability of success right there, right? So that's my little p, right? So little p equal to 0.9. 200 smoker 20 years old or older are randomly selected to find the number of smoker who started smoke before 21 years old, right? 5, so that would be my means right there, my sample size right there, right? So n equal to 200. So find the mean and the standard deviations of the 200 smoker who started smoke before 21 years old, right? So this one's okay. So mu equal to n times p. So we take 200 times with 0.9. So that would be 180. And the standard deviations, which is np, and then 1 minus p, and then square root of that whole thing. So 200 times with 0.9, and then 1 minus 0.9. Right, so everything's underneath the radical. So we get square root of 18, and that gives us 4.2426. So that's the mean, and that's the standard deviations. Now, what does that mean? It means that out of 200 smoker, we expect 180 to smoke before the age of 21. So that's what I mean by the expected value, right? Of the mean. So out of 200 smoker, we expect 180 to smoke before the age of 21. So again, this is all theory, okay? So this is all theory, right? So now that we have those information, we said, let's go out there and start asking people to see how the actual data compare with the one on the theory. Yes, right? So on your desk, you say, well, I want to show whether it's true or not, right? Said, I'm gonna go out there and ask 200 people to see how many actually smoke before they turn 21. before you go out there, you should have an expectation, and that's when you find the mean. So after you find the mean, you have that information said, okay, now I have the expectation that roughly 180 of them will answer, yes, I smoked before the age of 21. That's what you're expecting, right? Everything's still a theory. Now you go out there and you ask people. That's what part B is about. If the result of the survey found that 168 out of 200 smoker who turn 21 years old or older start smoke 21, is this result unusual? So talk about the unusual event, we're gonna go back to the box right here, right? All right, so any event that's occurred outside of the 95%, it will become an unusual observation. Okay, so we're gonna use that logic to help us finding out whether an event are usual or unusual. Okay. Okay, so based on that, right? Based on the definition of unusual. So anything outside 95%, in other words, mu minus 2 sigma to mu plus 2 sigma will be considered as unusual. Okay, so that's all we have to test. We have the mean, we have the standard deviations. We want to see what's going on, right? All right, so from part A, mu minus 2 sigma is equal to 180 minus 2 times with 4.2426. We expect to get 171.5148. And then mu plus 2 sigma will be 180 plus 2 times 4.2426. So we get 188.4852. Okay, so this is what we can make a discussion, right? So any number less than 171.5148 or larger than 188.48652 will be considered as unusual. So, yes, Matthew.
Just kind of off topic. Are those studies that you use, are they actually real studies or are they just random numbers plugged in?
Oh no, this is collection from the American Lung Association. It's
Okay,
real.
so I just want to make sure they do actual numbers.
Oh no, I cannot make up any of this stats.
Okay.
Yeah, you know, for algebra, I can just change it and make it look a bit different, but for stat, it's gonna be a real data. Yes.
Okay, thank you.
Yeah, so that's one reason why people believe in stat a lot, because it's all real data they collect. Yeah. Okay, so so to answer this question, the one we found, is that unusual? The answer is yes, right? Because it's less than 171, therefore an unusual, right? So the survey since 160A is less than 171.51 for A. So therefore the survey is unusual. I mean that it's not normal. Yes, Edward.
So here's where we can see the, I'm not too sure if this is the correct term, but here's where we can see the bias of the bell curve, where we get rid of the 5% to be considered as unusual.
Yeah, so they said, okay, if we can gather the whole group within 95% of the bell curve, then it should be good, right? Meaning that anything else outside of that range we'll consider to be too good to be true, right? So that's something wrong out of that, and that's what they stated this one here, right? Because according to that rule that we have, right? So anything like outside of this interval might consider, because the observation of curve will be less than 5% of the time, right? So therefore, we don't want to take that chance. Meaning that it's not good observation for the study anyway. That's what they meant.
So would you say that, would you say that I'm correct, that this is some sort of bias or no?
That's right. That's right. Meaning
Okay.
that we need to redo our survey.
I see. Thank you.
Yeah. Because think of the logic, right? Because when you take the probability of success is 90%, and that's the real data in the past, Edward. And if we think that I'm going to select 200 people, you're expecting around 180 of those gonna answer yes, we smoked before we turned 21. But now when you go outside and ask them, right, 168 only, you feel that something wrong here, yes? Because when they did the survey in the past, Edward, they don't do it for 10 people or 20 people. It's American Lung Association. They probably do for probably a few thousand people. So the data very, very true. So when we did it on our own, we only get 168. It could be a case that there are some respond bias because they smoke before they're 21, but they don't want to answer that, right? So we talk about respond bias in section 1.5. Does that make sense, Edward?
Yeah, that makes sense. Thank you.
Thank you. Okay. So if you see a question on the homework or on the exam where they mention about is it result usual or unusual, and this is all you do, right? So anything outside of the 95% range will become considered as unusual. So the only way to prove that is you do mu minus 2 sigma and mu plus 2 sigma, and then compare the result we received together with the ranging, right? So if we can satisfy that, then we're good. If not, then this is unusual, okay?
Now, this mu minus 2 sigma and mu plus 2 sigma will work even if the distribution is not bell-shaped.
No, it's only work when it's a bell-shaped.
Okay.
So that's why it's very important here that we stick to the empirical rule.
Okay. And then will we be given questions of distributions that are not bell-shaped?
No, it's going to be bell-shaped because this is how we verify that. Okay, we forgot to verify that, but when you do n times p, right? When you do np and then 1 minus p, so you take 200 times with 0.9 and then 1 minus 0.9, and this gives us 18. So that's bigger than equal to 10. So that's tell us that we can use the bell-shaped.
Okay.
Uh-huh.
And then that second qualification, if the little n is, I think it was less than or equal to 0.05 big N, what is little n and big N?
I'm asking you.
Oh, I don't know.
Okay, what's little n stand for, Grayson?
Number?
No. Can anyone help Grayson now? What's leader N stand
Please.
for?
Number of trials.
Number of trials.
That's right. And what's
Oh,
capital N?
okay.
What's capital N stand for?
Oh,
Population.
Populations.
Oh, I was right.
Oh,
Right. Little
Yeah.
n is a sample size, and capital N is a population, right? So, when you select 200 people, our 338 million is for sure less than 5%, right? So the second condition telling that the sample is less than or equal 5% of the population. That's what it is.
okay.
Yeah, it's take a while to grade it. Oh, capital N is a population, right? So we don't talk about that too much. That's why we kind of forget what's capital N stand for. All right. Okay, does that answer your question, Grayson?
Yes, it does. Thank
Yeah,
you.
good that you pull that up so that we all be clear, right? So it will only work when you have a bell shape. And to check out the bell shape, we need to see that when you do NP 1 minus P, that should be bigger than 10, and that's just a requirement of that. Yeah, sometimes we don't focus on the second condition too much because anything that we select will be for sure less than or equal to 5% of the population. Yeah. So you have, 300 million people, 5% of that, already like 15 million people, right? So we select 200. That's nothing compared to 15 million. Yeah. Okay, sounds good, guys. There we go. All right. And congratulations, you just finished half of the semester. Okay. Tomorrow we do nothing besides reviewing. So for that to work, I want to make sure that you go through the exam review package and do it. So I can only answer the question that you got stuck on. But I don't want to spend time the whole period to go over 47 questions. Okay. I want you guys to give it a try. Okay. You can put the homework aside. You can do the homework on Friday and Saturday. But the exam review, make sure you do it by tonight. Can you do that? And that's the reason why I uploaded by Monday already, right? So on Monday, I already upload that so you can already get a head start on that. Good to go. All right. So let me take attendance real quick, and then we'll see who's here. All right. Ian's Abrika here. No, Grayson's here. Adam.
I'm here.
All right, thank you. And Matthew. Thank you. Jackson.